So today I want to answer some of the really big questions about programming, which is things like, how do we actually know anything really works? Similarly, we've been talking about version control in the last couple lessons, so how do we know that this version of the software works the same as the previous version of the software? And since we're evolving this software over time, how do we safely extend the software without actually breaking it? So we're going to answer all three of these questions using testing. Specifically, we're going to refine the testing approach that we saw last time as a way to automate some of the tasks that we were doing previously. So you might imagine the first step I'm going to do is open up a terminal, make sure I'm in Ubuntu, figure out where I want to work today, which I have an i211 directory. Inside of i211 is my Hazel i211 starter, so I will cd into that. Now all my files are here, so I will do code space dot to open that up in Visual Studio Code. I'm probably not going to need this terminal for a moment, but I might need some of these other things. So let's do Control B to see where I am. I've got my test RPS, and I promised you last time that we're going to start thinking about what is this actual file doing. But maybe for now, I'm going to do Control Backtick in order to open up an integrated terminal in Visual Studio Code. Maybe make that a little bit bigger just to make sure that all of you can see. There we go. That should be a little bit better. Okay, and I'm going to work in this integrated terminal for just a moment. So today I want to create some notes. So let me do make.dir notes, and I think we're in lesson 5. So inside of this notes directory, maybe I'll just do a file called lesson05.py. I'll also do maybe touch test lesson05.py. Okay. We're just kind of adding files at the moment. This would be a good time to make a commit as well. If you want it to do this as well, you can kind of follow along. Whoops, excuse me. Git status, so the current directory is not being tracked. If we do git add everything, if we do git status again, we have 2 new files. So let's make a commit right here where we say add, actually sparkle emoji, because we're doing new things. Add new files, lesson05 and test_lesson05. Close out the double quote, enter. Okay, so what are we doing today? So, well, let's do Control P, open up this lesson05.py. Maybe I'll even do split screen with Control \, and I will do test_lesson05 right here. Okay, so right here we have tests for lesson 05. On the left-hand side of the screen, maybe we can say that we're going to have some lesson 05 notes. Let's see what happens when I run both those files. Make that a little bit smaller. So Python 3, lesson 05, Python 3, test lesson 05. Okay, this will be a pretty good foundation that we can do the rest of the material on. So let's go back to the notes for today and figure out what do we want to talk about. Cool, so back over here. Okay, so we're going to go from manual, from manual to automated testing. And I want you to imagine that you have a prompt kind of like this. So this tells you to create a Python script called sketching.py. Inside of it, we're going to define a function called mySum, which takes a list, which is a list of integers, and it returns the sum of all integers in the list, such as this thing right here. So the empty list should return 0. The list containing a single element should return 1, and the list containing 1, 2, 3 should return 3 plus 2 plus 1, which is 6. So that probably gives us pretty much everything we need. Maybe we can kind of skim down here and see that there is a solution, which I'll just go ahead and copy, because the solution itself isn't quite as important to this problem as the testing method itself. Let's make that a little bit smaller so it's still easy to see things. Okay, so if you follow along with the book, it's going to suggest that we have these two things. We have a mySum, and then we have a mySum, and we want to figure out whether or not this is correct. So on its own, if we just run lesson 5, notice that there is no main block. So we define this function but we never run it. So just invoking this script on its own is going to do nothing. How do we know this works then? Okay, well, we have 2 options. Maybe we do something like if dunderName equals dunderMain, then maybe we just call like the mySum function a couple times. So copy the mySum function. Maybe we will call this with the empty list, kind of like we saw a second ago. Maybe we call this a couple other times. So then with 1, then 1, 2, 3. Let's see what this does. Okay. So we have 1, 2, 3 function calls. So when we run lesson 5 now, we probably are going to see 0, 1, 6. Let's see if that's what happens. Yeah, so 0, 1, 6. So here's the first way that we could have tested. Let's call this the, the main block manual testing approach. What's the opposite of this? Okay, well, the other version is that we know that we have a REPL inside of Python. So what if we do something like start up a Python 3 REPL, and then maybe inside of this we could say from lesson 05 import my sum. Okay, well, now we have my sum inside of here. We can call it with the empty list. We could say, what is my sum of 1? We could say, what is my underscore sum of 1, 2, 3? Okay, so this is also another way to test, and maybe we'll call this like, like the REPL approach to manual testing. So we have two different ideas. We could do this thing where we first import some code and test out whether or not the function is meeting our expectations, or we could have just written a little bit of testing code inside the body of the function, and then when we ran it, we can pretty quickly ascertain whether or not it's meeting our expectations. So both of these ideas together basically hints at what this automated testing approach is going to look like. So for both cases 1 and 2, there was some expectation. So here's kind of one of our keyword, the expected result of what should happen, which we could verify by actually running the code. So now the next idea that we want to explore is, what if we could automate this idea, or at least create something that is good enough that we can get some instantaneous feedback for whether things are working correctly. So I have a couple hints inside of here. I'm going to modify this by copying, going back into Visual Studio Code, dropping that in here. We don't have a sketching module because I named things slightly differently. In this case, we have something called lesson 05. And notice, this is pretty much exactly what we had a second ago. So previously, we were calling this mySum thing, but now we're doing this extra step where each time we have one of these things, we are asserting that calling the function is equal to something else. So what do we think is going to happen if we run this test lesson 05 py inside of the console? Well, let's find out. Let's open it up, maybe clear the screen. If we do Python 3 test underscore lesson 05, did something happen there? I want you to think about this for just a moment. So I did just run the script, and we think that it is running all these assert statements. So is something actually happening? And maybe this is a good question for the audience. Is it a good thing that nothing appears to have happened? What do you think? So I ran the code and you didn't see anything. Is that a good thing or a bad thing? Okay, well, I always say that the great thing about computers is that we can just kind of keep writing code and find out, because we can get instantaneous feedback. So what if we add another line where we say that what happens if we assert that my underscore sum of the empty list equals 25? What do you think is going to happen if we run the code again? Okay, so nothing happened when we ran just these lines. What happens now when we run the code plus this line that looks a little bit suspicious? Well, let's find out. Python 3 test underscore lesson 05.py. Ooh, okay, cool. Let's zoom in on this idea. Okay, so now something happened. We got a traceback where it says that it tried to assert my sum of the empty list is equal to 25, and Python raised an assertion error. So what is an assertion error? An assertion error is a hint that there was a violation between what we expected to happen and what actually happened. Okay, so back over to the book. Okay, so what we did is we did something called create a failing test. And sometimes this can actually be super useful because it kind of shows us whether or not our expectations are actually valid. So sometimes it can be useful just to kind of assume that things are working, and then you add something contrary to that, and if the expectation fails, then you learn something out of it. So this thing right here, this idea that we can define some assumptions about what we expect to happen, is the key idea behind something called unit testing. So in unit testing, one isolates parts of the whole source code into discrete units of expected behavior, often at the level of functions. Those units are tested with more code, functions that answer whether or not other functions are behaving as expected. And maybe a quick caveat, because I think this kind of confused me for quite a while myself. We're going to use the word expected behavior pretty consistently instead of correct behavior. But in a sense, we can kind of point to the two things as being really the same. So correctness, if you remember from some of maybe your I211 and your proof concepts, correctness is often like a mathematical fact about the things that we look at. So maybe you talked about proof by induction. Maybe you talked about proof by contradiction when you were doing some of your discrete math stuff. So if we were to list out just a finite number of cases, oftentimes this is not necessarily the same as proving the absolute correctness of our code. Nevertheless, this unit testing approach does tend to be pretty effective at a lot of the things that we will encounter as programmers. So for example, how do we actually know anything is going to work in the first place? Well, we can enumerate some of our expectations in code, and then we can say, if the tests pass, then maybe it's working. How do we know that two versions of the software are working the same? Well, inside of this Git framework, well, we can just ask if the tests pass on one case and do the test pass on the next instance. How do we safely extend the software without breaking it? Well, if we have a set of tests and we have some way of maybe monitoring the state of our tests over time, if we avoid making changes that break our tests, then we're probably going to be pretty good about backwards compatibility with the software as a whole. So now our next step is to kind of think about what does unit testing in Python look a little bit more generally like. And well, the short answer is that we are not or rather, I am not the person who invented this. You are inheriting a large amount of knowledge that has previously been actualized inside of Python standard library in the unit test module. And the key idea of a few of these things is that a test file is usually prefixed. Actually, don't quote me on this just yet. Maybe I'll test that later. So a test file is prefixed with the name test underscore, and it contains something that kind of looks like this. Okay, so maybe there's some things that aren't necessarily going to be the most familiar. Like, okay, let's see. We have this thing called a class. Inside of the class, it looks like we are, okay, so we're doing something called extending right here. We have this thing called self right here. And then we're doing something called like self.assert equal mysum 0. Okay, so here's kind of the thing with this. The class is kind of incidental to this whole exercise. We're going to break this down and focus on just a couple of the key concepts, and then you'll kind of see that the class is really kind of boilerplate, which maybe I'll quickly mention that. So a lot of the time in programming, we say that boilerplate is something that is kind of necessary to write just as kind of this artifact of how a library or how some of the other code is written. It's necessary to actually get things working, but maybe you don't have to necessarily understand all of the boilerplate and details in order to use the artifacts. Okay, so let's kind of go back down to our example, which is that we have this thing that we were previously using this kind of manual assert statement approach. But what happens if we use this unit testing approach? So I'll copy all of this and let's just kind of start building up a solution. So I'm going to comment these out for just a second. I'm going to minimize the terminal, maybe make that a little bit smaller. Okay, so how might we fill in some of the gaps inside of this implementation in order to test this stuff automatically? Okay, well, we do need to import the module that we're testing. So that's pretty much what we had a second ago. I'll cut this out. I will replace this import line with that section. Okay, so now I actually want to kind of work my way in and then toward the outside. So assert equal. Well, okay, so that's pretty similar to what we had right here. So what if I take this thing right here, and it looks like we're asserting one thing is equal to another thing. Well, okay, we've seen that before. What if we just kind of cut some of this stuff out, paste it inside of here? Okay, and now we're on to something. So now we have a function which is asserting that two things are equal to two other things. Okay, so it looks like, and here's kind of the cool thing, and the reason that I was hinting that a lot of this really comes down to boilerplate. The function name is, in principle, not really all that important. I could just fill this with gobbledygook right here. I could fill the class name with gobbledygook right here. And technically at this point, it is functional, sort of. Actually, ooh, interesting. Wait, why did that not? Oh, Python 3, test lesson 05. Ooh, okay, hold on. We're doing this live, so I think there's something that I'm not quite picking up on. Okay, oh, no, this is actually an important point. Okay, so we ran 0 tests. Why did we run 0 tests? Okay, so there is one thing that is important, which is that on line 10, the name of this function does actually have to be named in a pretty specific way. So what if I call this test underscore da 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 da? Give it a save. Rerun the test lesson 5 in the console. Okay, so now since we prefix the name of this with test underscore, now we actually ran a test in 0 seconds, and it shows us that that test is okay. Okay, so in a sense, the names do not matter. In another sense, the names 100% matter. So test gobbledygook is probably not the best way to phrase this. So let's call this something like test sum of empty list is 0. Okay, so we have a human readable name of what this test is trying to accomplish. What if we just kind of keep repeating this a few times? So previously we had like, what, 3 things that we were asserting? What if we just kind of paste a few of these things in here so that we test multiple things? So in the first instance, we test that the sum of empty list is 0. What if on the next line, so let's replace this right here, we cut this out right here, we put that in there, let's just keep doing this, kind of just following a pattern right here, drop that in there, we assert that that's going to be equal to 6. What are each of these things trying to accomplish? Okay, well, on the first one, we are testing that the sum of an empty list is 0. Maybe on the next one, we are testing that sum of one element is itself. Okay, and then maybe we test the sum of 1 underscore 2 underscore 3 is 6. Okay, so now we have 1, 2, 3 functions. If we were to run the unit tests again, so let's do Python 3 test underscore lesson 05. So previously, let's do some pattern matching. So when we previously only had one thing right here, so when we had only one function, it said that it ran one test. What do we think is going to happen now that we have 3? Okay, make a guess about what you expect to happen next. Okay, and we're going to hit enter. Okay, we ran 3 tests in some number of seconds. We got 3 dots printed out to the console. So what this is telling us is that each of these periods represents a test that was ran, and it's going to give us some feedback that it ran these number of tests in some period of time and that everything is okay. Let's repeat that thing that we did earlier, and then we'll talk about this thing. So what if we add a failing test, just to kind of see what happens? Well, what if we test the sum of 1 is 0? Okay, well that sounds a little bit silly. So what would happen if we asserted equal that my underscore sum of 1 equals 0? Okay, so obviously this shouldn't work. What do we think is going to happen? So we previously had these 3, and it passed. 3 tests pass. What do we think is going to happen now that we've added this, what's that word we used earlier? A failing test? What do we think is going to happen once we run this code now? Well, again, computers are great. We can get real-time feedback just by running the code. Okay, cool. So what happened? Let's take a look at this. Oh, go back to my terminal. Sorry about that. Okay, so just a moment ago, we saw 1, 2, 3 things. Now we have this extra thing that happened. Let's actually kind of zoom in on this. Okay, so we have 1, 2, 3 periods followed by an F indicating a failed test. What is it that failed? Well, this test the sum of 1 is 0 is the problem, and we tried to assert that 1 is equal to 0, but in fact the opposite was true. So this is showing us that if there is something that is incorrect inside of our unit tests, then we can get some instant feedback as to what the problem is and where the problem is. So in this case, I do not need this incorrect test. And if we run it again, we get back to the situation where all of our tests are passing. Okay, so finally, what are we doing with this thing? Okay, so this class name is representing like a test case, where a test is a group of related things. So perhaps we could call this something like test sums of lists or something along those lines. So if we are testing that multiple sums of the lists are equal to some things, the overall group of test cases is going to be what is inside the class name, and then each of the individual methods inside of that are going to be individual tests for some behavior. So let's kind of review what we've had so far in the book. The way we phrased this here was that there's kind of 4 questions that we're trying to answer when we're writing these things, if we want to start from a template kind of like this. The first question is, what module are we actually testing? Next, we're going to say, what fact do we want to assert? Then we're going to say, what is the fact that we are asserting? So this is what I named some of these individual pieces, and it looks like I named things kind of differently in both of these cases. So like test summing 1 is 1. I guess down here, test sum of one element is itself. Well, that's kind of par for the course. I don't necessarily name things the same every time. Then question 4, what group of behaviors are we testing? Which is going to end up being this thing that we have the class name. So looks like previously I named it summation test. I actually kind of like that a little bit better, so maybe I'll say that summation test is what we're trying to accomplish right here. And then finally, putting the pieces together with these 4 question answers, we have a complete unit testing script, and we've, well, I guess we already did convert all of our remaining stuff into assertions, so this is probably going to be a pretty good case to, actually it looks like we covered most of this. Okay, cool. So let's do a quick review. So running the unit test and observing behavior, well, that's what we were kind of doing over and over again right here. So test underscore lesson 05 gives us instant feedback. If we were to add a failing test, then we get instantaneous feedback for what that kind of stuff looks like. So now let's talk about like, how do we actually use this in the wild? So what is some of the goals of actually using this stuff? So where I'd say this comes in, and let's kind of talk about Git again real quick. So we've currently modified both of these things. If we were to say git status, maybe git diff between lesson 05 and what we previously had, there's quite a bit of stuff that's actually changed between these 2 cases. So let me go ahead and add these 2 things and maybe say git commit-m add definitions. Let's see, add my_sum and tests for lesson 05. Okay, so we've made some changes. Now, one of the things that I mentioned earlier was that testing really makes sense alongside some of these version control paradigms, where we can make some assumptions about what our code should look like over time, and then we can test those. So at the moment, if we run the tests for this lesson, then it looks like it's okay. But here's the question. What would happen if something changed out there in the world and suddenly there was a new piece of behavior that we had to incorporate? So imagine that something changed out there in the world, and all of a sudden there's this new behavior that we have to incorporate. So my sum none should be equal to 0. Okay, well, what happens currently? Let's find out. So Python 3, what if we do like from lesson 05 import my_sum? Okay, so we know already that my sum of 0 should be equal to 0. But what does happen if we run the code to say my sum of none? 3, 2, 1, what do we expect? Okay, so there's a problem. Let's zoom in on this one. Okay, so we get a traceback. And it looks like on line 1, okay, so we're going to line 1, and then I think we're going to line 4. So line 4 of the lesson05.py has a 4x and LST, which raises a type error. None type object is not iterable. Okay, so there's a paradigm that we can kind of follow right here, which is, sorry about that. So there is a paradigm we can follow here called test-driven development. Let's see. To be fair, I'm not a huge fan of this paradigm. A lot of the time I think it's a little bit overcomplicated, but it's worth at least kind of being aware of this and kind of seeing what it looks like in practice. So the idea here is that if we have a new behavior that we want to incorporate, instead of using the function design recipe, where we normally say in step 6, test the function, in a test-driven development workflow, we actually say that we want to write the test and then implement behavior. So what does that look like in this case? Well, we know that there is this new behavior out there in the world. It's right here. So how would we validate that this would be something that now we want to incorporate? Well, what happens if we write a test for this? So maybe say that test the sum of none is 0. Let's do self.assert equal my sum of none equals 0. So I bet, since we just a moment ago said that raised a type error, what happens now if we run the unit tests for lesson 5? Well, we actually get the same information, but now we get it in the context of actually running the tests. So this is the same information. Line 4 inside of lesson05.py, inside of my sum, we get that type error that says for x and LST. Well, when when LST is bound to none, none is not an iterable object, therefore we cannot run a for loop over it. So this kind of hints at what the next state should be. And this is one of those cases where if I'm following test-driven development to the letter, we might say, okay, well, git add test lesson 05, git commit -m, add a test for the next behavior. Okay, git status, now I'm ready to implement something. So maybe the easiest way that I could validate this is that I could say, well, out equals 0. What if we say if LST is none? Well, if the LST is none, then we can just return 0 immediately, or maybe we can just say return out immediately. And question, do you think, now that we've implemented this, that the test will pass? 3, 2, 1, let's find out. Yay! Okay, cool. So here's the workflow. We modified the code, or rather we wrote a test, then we modified code, 3 tests pass, exclamation point. So that means that we accept the solution. So accept solution. Okay, cool. So let's do git status. Let's do git add lesson 05, git status again. Quickly make sure that it is currently in our staging area. It is, so let's commit and say add handling of none in my_sum. And as I did that, I realized there was actually something that was subtly wrong about my implementation, which is that it still says, according to this function signature, we are only reasoning about when my sum takes a list of integers and returns an integer. But there is actually something we have to update, so I am going to modify this as well, just because I like being real pedantic about my types. So now my sum either takes a list of integers or it takes none. Okay, so let's also make sure that this is correct. Git status. Yep, we've modified lesson 05. How did we modify it? Okay, well, we previously had this signature. Now we have this signature. So let's say git add everything, git status, git commit -m, just function signature. And I probably should have checked that just to be safe, but the tests are still going to be passing because a lot of this function signatures inside of Python are, well, they're really guidelines until you use something like MyPy. Okay, so it looks like we kind of incorporated most of these ideas. We failed a test, we adjusted the definition, and then eventually our tests passed. So now I want to talk about refactoring really briefly, actually, where refactoring, which I think I promised last time I'd talk about, is a change made to the internal structure of a software to make it easier to understand or cheaper to modify without changing its observable behavior. Or refactoring is to restructure software by applying a series of refactorings without changing observable behavior. So refactoring is kind of a big topic within itself, and we'll kind of cover some of the Spark notes. So really briefly, part of the way that we were mentioning this idea of testing and validation is that we want to be able to write software but not break things. So one of the ideas here is that once we have everything encapsulated within inside of a function, and once we have some tests that are asserting that that behavior is correct, one of the ways that we could think about writing software and extending it over time is that we can make sure things are backwards compatible, and simply by running the tests, we can answer whether or not our expected behavior is still consistent, even if we completely change the way that the function is written. So just as an example of this, what would happen if I were to replace this thing that I wrote a second ago with this definition? So this is a very different way of thinking about the implementation using a recursive solution. So is this the same? So is this completely different looking implementation where, notice we said, okay, get diff, make that a little bit bigger, a little bit easier to read. Yeah, okay. So is this thing right here going to produce the same behavior as this implementation right here? Well, let's find out. Again, great thing about computers is that we can just kind of find out by testing. Okay, so Python 3 test lesson05.py, and sure enough, it looks like we were able to completely change the definition of my sum without actually breaking the tests. So this kind of hints at how we might extend some of our software over time. Let's do git status, git add lesson05, git status again, git commit -m, change, or rather, let's do recycle for refactor, refactor to use recursive solution. Okay, git status. Okay, 6 commits ahead. Okay, so we bring up some of these ideas because this is going to be a problem that we're going to be revisiting over and over again for the rest of the course. Programming itself is a pretty hard thing, but maintaining software tends to be a lot harder. Because as we progress through this course, we're going to write code, but we're also going to have to contend with the burden created by that code that we wrote earlier. So all of these things that we talk about, documenting, testing, refactoring, version controlling, all of these are methodologies that evolved in response to the challenges people faced when they tried to maintain code with millions of lines. So we'll see a fraction of these as we progress in the class towards our final project. So now that we've seen quite a bit of this stuff, I want you to practice unit testing with that rock, paper, scissors implementation that we were working with last time. So there's the steps are hopefully laid out pretty effectively here, where we're going to apply a few of these approaches. And then at the very, very end, we're actually going to push up to GitHub and create a release of this stuff that we've been doing so far. We'll call this the v0.1.0 release of our code. So this would be a good time. I'd really recommend pausing the video here. So pause the video here, see if you can kind of anticipate some of the ways that I will approach things, and then maybe kind of see how I do stuff at the end. But if you do want to kind of follow along with me, I will give it just a moment and start applying some of these steps to show you how I would approach some of these as well. So 3, 2, 1. Okay, so if you're hearing my voice, I'm guessing that you're ready to kind of move on. Hopefully you've done a few of these so far, and you're kind of ready to see how I would approach some of these steps. Okay, so in this case, I've really already done these steps because I am already in my i211 repository. I'm going to close out of both of these, maybe get a feel for where I am. So we have this RPS file, we have this test RPS file, which I'm going to open up in 2 tabs next to one another. Oops, I accidentally created a breakpoint right there. Minimize that. Okay, so here's the goal. We have this RPS implementation, and we want to write some unit tests for it. So let's see what the first one is. Okay, first step is to run the tests. So notice, I am actually in this notes directory. So my first step is that I need to go down one directory. So I'm right next to all these other pieces. If I were to do Python 3 test RPS right now, then it does say that I ran a test, but this isn't actually a very good test because notice that I am just asserting that true is true, which is, well, vacuously true. Okay, so validate that rock is a valid input. We can do this a couple of ways. So we could say something like from RPS import is valid, and we of course can say that is valid rock. Yes, absolutely, rock is a valid input. But how do we actually go about testing that? Okay, well, we already have this validate human input section, which, I guess I could just uncomment this line, rerun the tests, and see that I do actually get something working. So let's see what the difference is. Oops, excuse me. GSD is a shell plugin that I have. Git status. Okay, cool. What is the difference? Well, okay, we replace that. So let's say git add test RPS, git status, it's in our staging area, git commit -m, or let's say tidy up, or excuse me, Ta-da emoji. Start unit testing RPS. Okay, we've created a commit. What is our next step? Okay, so validate scissors and paper. This is pretty much going to be exactly the same as we had right here. So let's copy this, paste. So now test rock is a valid input. Test that's a valid input. I'm going to do a cool trick, which is Control D. So now I can say test scissors is a valid input. Let me do that a little bit slower in slow motion with the next one. So I select rock. Notice that rock is selected, or kind of ghost text in both of these. If I do Control D, now I can do PAPER, and I can rename two things at once. What happens when I run the tests now? Python 3, test RPS. Okay, 3 tests ran. That's a good time to add that stuff in. Confirm that test RPS is in my staging area. Let's do git commit -m, add, or let's see, what's a fun one for this one? I think it's a checkbox. Yeah, green check. Add 2 tests for validation. Cool. Okay, what's our next step? Because we verified this already. Oh, stage and commit. Okay, well, I've actually been kind of doing this. You'll kind of get the feel that I tend to make a lot more commits than is probably necessary, but that's just because I like being able to jump back to different points in time. Okay, so how would you test the computer choice is kind of our next question. So inside of rps.py, we have, let's see, let's go down. So get human input, get computer input. Ooh, okay. Let me take a look at something real quick. So notice that this is actually slightly different from the way that I implemented my code. So you don't have to do this if you want to stick with the way that you named things previously, but I am actually going to refactor this so that I have get computer choice and therefore get human choice, just to make sure that things are pretty consistent. Really, that's just to make sure. Okay, so I renamed those two things. Let's make it so get human choice is called right there. Get computer choice is called right there. Let's just kind of scroll up, scroll down, make sure that we don't see any of the yellow squigglies. Maybe kind of excuse me. Maybe kind of manually test that my RPS implementation is still working okay. Yep, okay, so it looks like that's mostly still working. Paper one more time, Python 3, test rps.py, that's still passing. Get status, let's say get diff rps.py. So there is actually a refactor for this. This is called a refactor rename. So let's do get status, get commit -m, recycle emoji for refactor, rename functions for consistency with the book. Really optional, but just because I'm demonstrating this and I want to have kind of consistent set of code, it's probably not a bad idea. Anyway, so back to step 6. So our possible suggested that computer behavior was all defined inside of this. Okay, so we have some choices here. This function does not take an input, but it does produce an output. What are the expected behaviors, and how might you test those behaviors are true? So I think I've got 2 solutions hinted at down here, but I'm not going to quite look at those. You can skim those in the book on your own time. So the way that I will approach this is, let's say that we are validating the computer behavior. What behaviors are we validating about it? Okay, so maybe we want to test the possible outcomes of computer choice. A little bit verbose, but that's okay. So what is it that we want to assert about this computer choice function? Well, we have, what are the possible return values? So this could return scissors. So this could return scissors, this could return paper, or this could return rock. So what if we actually kind of assert that idea in code? I think this is probably closer to what the alternate solution is mentioning. But what if I actually use a for loop inside of this? And side note, I'm kind of drawing some inspiration from something called property-based testing, where in property-based testing, you're usually looking for properties of the outcome function rather than a specific output. So maybe what I want to do is I want to say for some number of iterations, so maybe for blank in range 25, why not? What if we self.assert true, and we say something to the effect of rps.getComputerChoice. Oops, try again, getComputerChoice, tab to autocomplete that. What if we assert that getComputerChoice is in the set of rock, paper, scissors. Okay, maybe try that again, drop that line out. Oops, I don't have a formatter. That's right, because I haven't told you what a formatter is yet. Okay, so let's modify that a little bit, maybe just make that code a little bit easier to read. Okay, assert that this thing is in that. Let's see if this runs. So if we do Python 3 test rps.py, okay, cool, interesting. Well, we're getting a lot of output. So maybe that's a hint that we're actually going to want to modify this a little bit at some point. But for now, all of the tests ran. So I am going to modify this very slightly because there are multiple things that we could assert inside of this. So if we were to do self.assert, okay, we actually have a lot of different choices that we can actually assert inside of this. I happen to know about one called assert in, and assert in is pretty much doing what we have here, except we can do it over 2 calls. So assert in, we do rps.getComputerChoice, then we will take this thing out, drop that down there, and let's see what happens when we run the code now. Python 3 test rps.py. Cool, looks like we're still passing. Let's do a tiny bit of cleanup. Let's see if we can make a commit. So git status, git add test rps.py, git status again, confirm it's in the staging area, git commit -m. Let's see, checkbox emoji, add tests for computer behavior. Confirm. Okay, cool. So run the test and commit. Yep, we've been doing that all along. Ooh, how would you test now that rock beats scissors? Okay. So we said that in our possible RPS solution that the core X beats Y behavior could be placed in a beats this that function. So how would we test this? How would we run those tests, and how would we stage and commit those changes? Okay, cool. So now we're kind of on our own on this one. Okay, so validate computer behavior. Let's just kind of duplicate a lot of this stuff. So now instead of validating computer behavior, we are validate X beats Y. I'm just kind of coming up with some names on my own. Okay, so let's do test rock beats scissors. Okay, so what would this look like? Well, let's just do assert true that rps.beats does rock beat scissors. Well, let's find out. Python 3 test rps.py. Yep, 5 tests pass. Let's kind of just repeat this 3 times. So 1, 2. So test rock beats scissors. Let's also test that scissors beats paper. So does scissors beat paper? And what's the last one? Test that paper beats rock. So paper beats rock. Okay, let's find out if that all works. So Python 3 test rps.py. Cool, 7 tests, all of them ran, all of them succeeded. Now let's go ahead and do git add, or rather git status. Let's do git add test rps.py, git status, git commit -m, new emoji, test that rock, let's see, test for rps.beats. Git status, update, head by 11 commits. Okay, so now we're pretty much done. I'm going to do that final step where I push and make a release. So try to remember, what do these steps look like? The solution is right here, but pushing, so pushing is pretty straightforward. That's just going to be git push. What does tagging look like? Okay, well, first we have to kind of remember how tagging works. I'm going to make that a little bit bigger, clear out the screen. Git status, just confirm that your branch is up to date with origin main, nothing to commit, working tree clean, which means that we are going to tag this state of the repository at this point. So let's just maybe see what that looks like real quick. i211su2024 / Hazel i211 starter. Okay, cool. So I've got about 15 commits out here. Maybe make that a tiny bit bigger. Nothing has been released yet, which means that I am ready to make a release now. So I'm going to say git tag. Where do I want to tag it? I want to tag it at version 0.1.0, and I need to supply a message. So I want to say something like initial release with tested RPS implementation. Cool. That should have created the tag. If I want to check that, I could actually just do something like git log -- graph -- one line. Don't have to remember that. but this is a quick way to visualize that I'm on main. I do have a tag at this point in time, which is up to date with origin main, which is my final commit for testing that RPS beats something. So last step, I'm going to do git push origin v0.1.0. Enter. Okay, GitHub responded by saying that I created a new tag at version 0.1.0. If I go back to GitHub, refresh the page, there is now a tag created out here.